Welcome back. Today I would like to talk to you about partial derivatives. And I love partial derivatives. They're kind of one of my favorite subjects in Calculus 3, so I'm excited to talk a little bit about them today. So let's just start out with a definition. So definition, the partial derivative of some function f of xy with respect to x at the point x0, y0 is. Now, we have kind of a nifty little symbol for partial derivatives to keep them straight from actual derivatives, and that is we use kind of like this little, it looks kind of like a D, but it's more of like a backward 6, I guess you could say. Partial of f with respect to x. Okay, so those aren't D's, they're, like I said, they are D's, but kind of think of them as kind of like your Greek D's of sorts. And so we've got at a point x0, y0 is going to be equal to the limit as h goes to 0 of f of x0 plus h y0 minus f of x0 y0 divided by h if the limit exists. Now, how is this different from a derivative? Well, a derivative, when we were working in 2 dimensions, we just had this f of x0 plus h. There was no y0. So what this is really doing for me is it's saying, hey, when we're in 3 dimensions, there might be more than one slope. Okay, what do I mean by that? What do you mean more than one slope? Well, think if you had, like, in 3 dimensions, a hill. Okay, so let me try to draw a little hill in 3 dimensions. So here's a hill, okay, but that hill has some depth to it, right? So let's imagine this hill, okay, and now let's take a point on that hill. Underneath, I want to draw an xy axis. So here's my x-axis. Imagine this is below the hill, and here's my y-axis. So I've got an x-axis, a y-axis. And now what I'd like to say is, okay, what if I have a point sitting on that hill? Okay, and this is the point that's x0, y0. I'm going to change colors real quick here, and let's use red to kind of represent the y direction. Okay, then in the y direction, this thing is sloped downward. If I were just kind of to measure this thing in the y direction, notice I might get a tangent line that looks sort of like this in the y direction. In the x direction, let me change my color again. In the x direction, if I'm measuring that, I might get a tangent line that looks sort of like this. It's hard to see the slope on these, but you kind of get the idea. If you're sitting on that hill, you get some sort of a tangent line in different directions. So there's a tangent line or a slope in the y direction, and there's a tangent line in the x direction. If you think about it up at the top of the hill, both of them would be flat. Do you agree that up at the top of the hill, I'd get a tangent line that's flat in the x direction, and I would get a tangent line that is flat in the y direction. So they're both flat. That's interesting in and of itself, right? And that will be useful to us later. But it could be different. You could, in some sense, maybe here on the edge of this hill, maybe in the y direction, it has a slope, some slope, and in the x direction, it's actually flat. Okay, so it has a 0 slope in the x direction, but it has some like negative slope, let's say, in the y direction. Okay, so the slopes don't have to be the same in the x and the y direction if you're living on a surface. So what these partial derivatives are doing for me is it's telling me the slope if you're moving in the x direction or the slope if you're moving in the y direction. And so the slope if you're moving in the x direction we call the partial of f, we call that the partial of f with respect to x, is if we are moving in the x direction, and if we're moving in the y direction, then we call that the partial of f with respect to y. So we have a tangent line in the y direction, and we have a tangent line in the x direction, and those are called the two partials. Now, what's so amazing about this to me, and what I really like about it, is how easy they really are to compute. So let me go back to white again, and let's do an example here. So, an example, let's find the partial of f with respect to x and the partial of f with respect to y at the point 4, minus 5 if the function f of xy is equal to x squared plus 3xy plus y minus 1. And the way that this is going to go is if I'm taking a derivative with respect to the variable x, then y is just a constant, and I treat it as such. And if I'm taking the derivative with respect to y, then I treat x as a constant. Okay, so you just kind of forget about the other variable and just treat it as a number. And so it makes it very, very easy. So let me show you what I mean. So let's say that I wanted to compute the partial of f with respect to the variable x. So what I do is I go along and I look at the first term, and I notice it's x squared. Well, just think about what's the derivative of x squared with respect to x squared. And we've done this all the time in calculus. The answer is just 2x. Then let's move on and look at the derivative of 3xy. Well, the only x in there is just x. So what's the derivative of something times x? Well, just the thing, right? The constant. But in this case, the constant attached to that x is 3y. Because remember, y in this case is just a constant. And now I need to take the derivative of y. But y is a constant. The derivative of a constant is 0, so plus 0. And the derivative of minus 1 is also just 0 because it's a constant. So I just get that the partial with respect to x is just 2x plus 3y. Okay? And what that does for me is that gives me the slope in the x direction of any point xy. So what I can do is now I can find, well, what's the partial of f with respect to x if I evaluate that at the point 4 minus 5. So plug in 4 for the x and minus 5 for the y, and I get 2 times 4 plus 3 times minus 5, which is 8 minus 15, which is negative 7. So the partial with respect to x evaluated at 4 minus 5 is negative 7. In other words, that's the slope of this surface in the x direction at the point 4, negative 5. That's cool. And the thing that's so amazing about this is it's really quite easy to do, right? Let's do the same thing for the partial with respect to y. Okay, so I'll just go ahead and erase really quick some of this, and because I want to use the exact same function. So now let's look at the partial of f with respect to y. So now y is the variable and x is a constant. So now if I'm looking here at taking the derivative of x squared, x is a constant. So x squared is a constant, so that derivative is just 0. When I move over here to the 3xy, y is the variable, and the derivative of something times y is just that something. So that's just 3x. The derivative of y is just 1 with respect to y, and the derivative of negative 1, that's a constant, so of course it's 0. So I just get 3x plus 1. So if I want to take the partial of f with respect to some variable y at a point 4, negative 5, then that's just going to be 3 times 4 plus 1, which is 12 plus 1, or 13. So the slope in the y direction at the point 4, negative 5 is going to be 13. Cool. Let's try another one. So example, let's find so the partial of f with respect to x and the partial of f with respect to y for the function f of xy is equal to e to the xy times ln of y. Okay, so now we have to just kind of remember how to take derivatives. There's really not a lot of difficulty here as long as we're paying attention to which one of these is our variable and how do we take derivatives. All right, so let's start with the partial of f with respect to x. And by the way, I'm going to give you a new notation here. One of the ways that we'll write this, just to save us time because I get tired of writing all these partials, is we could write it this way. We can't write f prime anymore, right? We can't write f prime because we don't know which variable we're taking the derivative with respect to. So f prime is sort of meaningless now, but we can write this, f, and then write a little sub x. And so I'm saying I'm going to take one derivative of f with respect to x as the variable. Okay, so in other words, f sub x means the partial of f with respect to x. So that's a new notation. And so let's do it. So x is the variable. So that means that this whole ln of y right here, that's just a constant. So the derivative of something times e to the xy, the constant can just stay around. So the ln of y will stay. And now I just need to remember how to take the derivative of e to the x times y. Well, the derivative of e to a power is going to be e to that power times the derivative of the power. But remember, I'm taking the derivative with respect to x, so what's the derivative of x times y? It's not a product rule, because x is the variable, y is not. The derivative of x times y is y. So the partial of f with respect to y should be ln y times e to the xy times y. Sound good? Okay, let's try the partial of f with respect to y. If I wanted to write this in my new kind of shorthand notation, I might write f sub y, which also means the partial of f with respect to y, and I get. Okay, so now this is a little more challenging because both the first part of this function and the second part of this function both contain y's. So this is exactly where I would need to use the product rule. So the product rule says I need to take the first one and leave it alone, so e to the xy. Then I need to multiply by the derivative of the second. So I need to multiply by the derivative of ln of y. But the derivative of ln of y is 1 over y, plus the second left alone, ln of y, times the derivative of e to the xy. But the derivative of e to a power is, just rewrite it, e to that power, times the derivative of the power. I'm taking the derivative with respect to y, so with respect to y, xy's derivative is x, because x is a constant. So the partial with respect to y would be e to the xy over y plus ln of y, e to the xy times x. And that gives us the partial in both directions. So that's kind of cool. Okay, let's try another. This works actually in, even if the function itself is written implicitly. Let me show you what I mean. So instead of writing this as f of xy, let's say that f of xy was represented as a z, and I have, if yz minus ln of z is equal to x plus y, then find the partial of z with respect to x. Okay, so I'm taking the partial of z with respect to x. Now remember, z is a function of x. Okay, we're treating z as if it's a function of x, and we're going to be treating y as a constant. So if I'm taking this partial, what's the derivative of this first piece? Y times z. Well, y is a constant, so I just get y. And the derivative of z with respect to x is the partial of z with respect to x. And now I need to take the derivative of minus ln of z. So the derivative, minus can just stick around. The derivative of ln of z is, by the chain rule, 1 over z times the derivative of z, which is dz dx. On the other side, the derivative of x with respect to x is 1, and the derivative of y with respect to x is 0. So now I just need to solve for dz dx. So I can factor out a dz dx on the left side, and I get y minus 1 over z equals 1. And so I get that dz dx is equal to 1 over y minus 1 minus, y minus 1 over z. And I have a formula for the derivative of z with respect to x, and that's a partial derivative. Okay, so in that case we would actually have to know the z value to find this because it's written implicitly. Just as in 2 dimensions, sometimes we have to know the value of y to find an implicit derivative. That's no different, but we can certainly use our knowledge of derivatives now to take partial derivatives both explicitly and implicitly. Okay, so that's kind of cool. Let's do another example. So let's find the partial of f with respect to z if f of x, y, z is equal to x times sine of y plus 3z. And we're trying to find the partial with respect to the variable z. All right, so nothing's changed really. We're working in one more dimension than we were before. But remember, if we're taking a partial with respect to z, then z is the variable. And x's and y's are just constants. So we just treat them as such. And we say that the partial of f with respect to z is going to be equal to, like I said, x, it's just constant. So let's just rewrite it as x. And then I have sine of something. The derivative of sine of something by the chain rule is cosine of that thing, y plus 3z, times the derivative of what's inside. So I want to multiply that by the derivative of y plus 3z. The derivative of y with respect to z is 0. And the derivative of 3z with respect to z is 3. So I get that the partial with respect to z is x cosine of y plus 3z times 3. Not so bad. Okay. Let's talk about second derivatives. We have second derivatives in 2 dimensions. In more than 2 dimensions, we have to be a little bit careful again because there are more than one derivative to take, partial derivative to take. So let's talk about what we would call the second partial of f with respect to x. The way that I would write this in my shorthand notation is I'm taking 2 partials with respect to x. Okay? And what's going to be important here is that we need to know which one comes first and which one comes second. Or we need to understand, does it really matter which one comes first or which one comes second? Because I could also write the partial squared of f over the partial of y, partial of x, which we would write as f sub x sub y. So in other words, the derivative that you do first is written first. The derivative that you do second is written second. In the case of 2 x's, it doesn't matter. In the case of a y and an x, it does matter. Okay, so we could say the partial squared of f, partial of x, partial of y. We would write this as f sub y x. And then partial squared of x partial y squared is f sub y. Okay, so those are 4 things that we should be aware of what they mean and which derivative gets taken first. And that is that the one that is written first is taken first. Okay, over here on this side, if I'm looking at this, the x comes first, then the y. Over here it's written the x comes first and then the y. So make sure to keep that straight. All right, so let's do an example here. So if f of xy is equal to x times cosine of y plus y times e to the x, then let's find a few things. First, let's find f sub xx, f sub xy, f sub yx, and f sub yy. Okay, so all the second order partials. Okay, so let's start with f sub xx. F sub xx, I need to, in order to find that, I need a first partial of x. So let's find f sub x. So f sub x here, let's look at the first term, and I have x times cosine of y. The derivative of x times cosine of y with respect to x is cosine of y. And over here, the derivative of y e to the x with respect to x is plus the y is constant, so it just stays, and the derivative of e to the x is e to the x. So that's my first partial with respect to x. The second partial with respect to x is the derivative of cosine of y. That's just constant because there are no x's, so that's 0. So the derivative here is 0. And the derivative of y e to the x with respect to x is y e to the x. So I just get that this is y times e to the x. Okay, now what if I wanted to take the derivative of the x first and then y? Well, I already took the derivative of x with respect to x first. That was f sub x. So now I just want to take this one and take its derivative with respect to y. Well, the derivative of cosine of y with respect to y is negative sine of y. And the derivative of y e to the x with respect to y is e to the x. Okay? So my first f sub xx, or the second partial with respect to x, is right here. F sub xy is right here. Now I need to know what's the first partial of f with respect to y. So go back up to the original and look at this guy. X is just a constant in this case, so it just stays. And the derivative of cosine of y is negative sine of y. And then if I want to take the derivative of the second piece with respect to y, the derivative of y times a constant is just the constant, so plus e to the x. Okay, so if I wanted to take a derivative of that guy, of the partial of y with respect to y, now with respect to x, so now I'm going to take the derivative of this with respect to x. Then I would just get negative sine of y for the first term, because that's the constant in front. And the derivative of e to the x is e to the x. And if I wanted to take the derivative of the partial with respect to y, then in this first one, x is a constant, actually negative x is a constant. And the derivative of sine of y is cosine of y. and the derivative of e to the x with respect to y is 0. So I get, this was my my third double partial, and this was my fourth. Okay, so I got all four of these second order partial derivatives fairly easily. Now, something to notice here are these two, that I have f sub x sub y and I have f sub y sub x, and they're the same thing. So the question is that true in general? Would they always be the same or not? It's an interesting question because one of them is the change in the y direction of the change in the x direction, and one of them is the change in the x direction of the change in the y direction. So are those two things the same, or are they different? This next theorem will answer that question for us. So, theorem. This is called the mixed derivative theorem. So the mixed derivative theorem says the following. If f of xy and its partial derivatives f sub x, f sub y, f of x sub xy, and f sub yx, if those are all defined throughout an open region containing a point AB and are continuous at the point AB, then f sub xy of AB is going to be the same thing as f sub yx of AB. Okay, so what this is telling me is answering the question I just asked. Is f sub xy equal to f sub yx? And the answer is yes, sort of. In general, for nice functions, it will be. If the function itself is defined around the point, so around AB, the function actually has functional values, and it's continuous at that point. Okay, so if it's defined around AB and continuous at AB, then those partials are the same. If not, maybe not. But for most nice continuous functions, you don't have to compute those two twice. The partial of xy and the partial of yx, that's the same thing. Okay, so let's do an example. Now that we know this, we can compute f sub x, x, y, y for the function f of xy is equal to x y squared plus x squared y cubed plus x cubed y to to the fourth. Okay, so we want to take the derivative twice with respect to x and then twice with respect to y. Let's do this. So first I want to take the derivative of this function with respect to x. If I do, the first term just is y squared. The second term is 2x y cubed. And the third is 3x squared times y to the fourth. Remember, no product rule because y's are constants. Now let's take the derivative again with respect to x. So the derivative of y squared is 0. The derivative of 2xy cubed is 2y cubed. And the derivative of 3x squared y to the fourth would be 6x y to the fourth. Now let's take a derivative of that with respect to y. So with respect to y, this is going to be 6y squared. And this second term is going to be 24xy cubed. Now let's take another derivative, again with respect to y, and I get 12y plus 3 times 24 is 72xy squared. So we took a double partial with respect to x and then a double partial with respect to y. Okay, let's do one more. So another example. Let's compute f sub xy for the function f of xy is equal to x times y plus e to the y divided by y squared plus 1. Now, remember, I can do this in any order I want to. I can either take the derivative with respect to x first and then y, or the derivative with respect to y and then x. But you'll notice that one of them is much, much, much better for me. And that is, let's take the derivative with respect to x first. Because if I take the derivative with respect to x first, then the derivative is y. Correct? Because the derivative of this whole second term is just 0. There are no x's. And then if I take the derivative of that partial with respect to y, I get 1. Now, if I would have done that in the other order, life becomes harder because I have to do a quotient rule with that second term. So you might want to, if you're taking a partial with respect to x and then with respect to y, you might want to look at the first function and say, what's going to make my life easier, taking the derivative with respect to the x first, or taking the derivative with respect to the y first. And since you can choose, you can make life as easy for yourself as possible. Time for some homework.